Okay. So, girls, I'm going to go over the two sims. I'm going to go over Blackbody Radiation, which is, I guess, where's the Blackbody Radiation one? Oh, here we go. Okay. And then we'll talk about the Photoelectric Effect, okay? So, you guys played around with this sim? Okay. What do you think was trying to be like portrayed in terms of the information? So what's going on in the simulation? What are you seeing here? What's a black body, first off? Something that can absorb what? Radiation, right? And so it's black because it's absorbing all the visible light. And when you heat it up, it will start to emit radiation, right? And what you're seeing here is the different wavelengths of light, visible and invisible, that you're emitting at different temperatures, okay? So, if the temperature is really cool, 300 Kelvin, that's about room temperature, you can see not much is really being emitted. So when we start to heat up an object, it starts to give off electromagnetic radiation, right? Now, sometimes you feel heat without seeing any light. Because if you'll notice, initially, the energy is here. So you see that? Very little, actually, nothing right now in the visible light spectrum, but we feel there's a little bit of a bump here. Does anyone know what this zone is called? Yeah, this is the infrared, right? So when you turn an oven on, you'll notice that it starts to glow. First you'll feel the heat, and then it starts to glow red. So you'll feel the heat, and then you'll start to see some red. Now, the ovens that you have probably won't, I don't know what colors they would go to. But if you could heat it and continue to heat it, you would start to see other colors. So why is a light bulb white? Because it's emitting what? Why is a white bulb white? Because it's emitting all the colors. Okay? If a light bulb was only emitting like an orange color, then that would be basically not all of the light being emitted. So that light bulb would be cooler. But as you start to see it drive towards like a white color.
Please excuse this interruption. If I could have everyone's attention, even those students in.
Okay, so you can see, like, for example, on this little thermometer here, that, you know, a light bulb will emit lots of color, but also lots of heat. Now, the LED light bulbs are a little bit different. They're much more efficient, right? But if you touched a regular light bulb and it was on, it would be really, really hot. And that's because you can see a lot of the energy that's being emitted is in the this is called the infrared, okay? This on the other side, this is the ultraviolet on this side. So you can't see the infrared, you can feel the infrared. You can't see the ultraviolet, you can feel the ultraviolet over time, because that's what gives you suntan. Yes, the ultraviolet light, which can't go through glass. So you shouldn't be able to get a suntan if you're trying to get exposure to the sun through glass, because the glass blocks it out. And then you can see as we drive this temperature up, okay, so like for example at the surface of the sun, okay, you can see there's a lot of heat, there's ultraviolet radiation, which is what's going to give you your suntan or your sunburn, okay, and there's also a lot of color coming out of the sun. Now, what was predicted to happen if something was heated? You guys, anyone do any research on this? No? So what you're seeing here is something called the ultraviolet catastrophe. The prediction was that if you were to heat something and continue to heat it, then what would happen is you would start to see a curve that would basically continue up to infinity. But that's not what happens. So in other words, instead of getting a curve that goes like this, you can see that it actually has a limit. So you're going to continue to heat this. You can see it goes up, but then it comes back down. And that was not predicted initially. Now, what's going on then? Why doesn't it do that? What do you think's happening here? Did any of you guys do any research on this stuff? Did I even ask you to do research on this stuff? What were the questions I asked you? What were the questions I asked you for blackbody radiation? Simulation. You can find simulation. You can anyone find it? You guys find it? No? Wow, okay, I'm getting like all these blank stares. Okay, so physicists at the time predicted something totally different. They predicted that if you were to take, look at my pen here. If you were to take my pen, an object and heat it, and you were to look at, so on the bottom of the axis was the frequency, and on the y-axis was the intensity. They had predicted this. Okay? Now, what does that mean? Take an object, you heat it, you start producing higher frequency light. Okay? So higher frequency light would be things with shorter wavelength. Remember the equation V equals F lambda from grade 11? So what are we talking about here? Speed of light. So F goes up, that means what? Wavelength has to go down. So as we go to the left, the wavelength decreases. So scientists predicted two things. They said if you heat something and you continue to heat it, then the frequency of the light coming out will be higher, which means the wavelength will be lower. Not only that, but then the object will start glowing more brightly, which is the intensity. And it will just continue to do this. But that's not what happens. As you can see in animation, it goes up, but then it comes down. So, and where it comes down, you can see it comes down in the ultraviolet region. So this was called the ultraviolet catastrophe. Because physicists are like, what's going on here? Why does it go down? Why doesn't it continue to go up? Why don't we continue to produce higher frequency light? What's going on? So that was the conundrum. That was the dilemma. So what's the solution? So along comes a guy named Max Planck, who was studying this. And he was studying this because he wanted to understand the light bulb a little bit better. He was hired to come up with a more efficient light bulb. Because you can see, the problem with a light bulb is a lot of the energy is wasted. As what? As heat. That's why there's this whole push towards more efficient light bulbs. You see most of the energy, you get some light, most of it is actually heat energy. So he was the one who was studying this, and he came up with a concept. And he didn't believe the concept that he came up with. When he came up with it, It took a few years later, Einstein looked into it and expanded on it. Okay? And he said this. He said that you can't think of the energy that's being released as continuous. You know how yesterday we talked about you got to think of it in terms of steps, right? He said the same thing. And this is what he said. He goes, the energy that's coming out is quantized. It comes out in discrete bundles of energy. So you can't just have any amount of energy. There are like limits to what you can get. So when you heat something, you will not just start producing any wavelengths of light. There's a limit there because there's only so much energy available because it comes in these packages called quanta. So he's the first one to come up with this whole idea of quantized. Remember, we talked about what quantized means, right? What does quantized mean? Yeah, like a package of something, right? The smallest indivisible unit. So he's the one who actually came up with this. He's the one who actually started a whole revolution of quantum mechanics. So you can think of physics before Planck as like classical physics, and then there's the physics after Planck and after, which is called the modern day physics, okay? Which includes this whole idea of quantized things, quantum mechanics. So he's basically saying that you can't just produce any wavelengths of light because they come in these discrete bundles. And he came up with so what he was trying to do is actually trying to figure out, he has this data, he's trying to make sense of the data. It's not a curve that continues forever. So he comes up with a formula to fit the data. You guys probably do this in math, right? You get like a curve, and then you get an equation or something formula to fit the data that you're seeing. So this is what he came up with. He came up with this equation. Now, I'm going to make this a little bit bigger so you can see it. Okay? So what he's saying, now this is the equation. This is the equation for energy. Okay? This is that quantized energy that comes out in bundles. And it can only come out in discrete packages. And the equation goes something like this. This is E for energy. Okay? And then you have this one. F is the frequency of light. Okay. Now, do you guys know the relationship between frequency and intensity? Sorry, frequency and energy. You guys know that relationship? We talked about it in grade 11. Might have. I'm pretty sure we did. So the idea is light that has a higher frequency has more energy. So light in this region has less energy because it has a lower frequency. Light in this region has a higher frequency, it has more energy. So the higher the frequency of light, the more energy it has. And if you need a reminder, just think about, okay, this is ultraviolet on this side, and this is red light on this side. And if I was shining red light on you, would you be worried? No, but if I was shining ultraviolet light on you, would you be worried? Yeah, because it's dangerous. So as we move to light that has higher frequency, like X-rays, then that light has more energy. You have to be worried about that. Okay? That can cause cellular damage. Okay. So what he's saying is that the amount of energy that you're getting out is quantized, and it's a function of the frequency of the light that's coming out. It's also a function of what's called Planck's constant, which he derived, okay? Here's the constant right here. It's a very small value. It's 6.63 times 10 to the negative 34 joules seconds. So joules times seconds. And then there's n. N is just an integer. Because it's quantized, you can only get multiples of this. Like one or two of these or three of these or four of these. Like, you know how we talked about the charge on an electron is quantized? So if you have one electron, if you have an excess of one electron, that's a negative 1.6 times 10 to the negative 19 C. Well, if you have two excess electrons, that would be 2 times 1.6 times 10 to the negative 19 C. Energy is exactly the same. It's quantized. So it's a function of Planck's constant times the frequency, but you can only have integers of that. So let me show you an example, okay? So let's imagine we had ultraviolet light, and the frequency of the light is 1 times 10 to the 15 hertz. Okay? And we want to know what is the energy of that light. Okay? What is the energy of that light? And for this one, we're going to assume n is 1. Okay? So E is H times F because n is 1. So H is 6.63 times 10 to the negative 34 joules seconds. And frequency is 1 times 10 to the 15 hertz. But what's a hertz? What's the actual unit of hertz? It's something per second. So you'll notice the time will cancel out. So you're left with this. Okay? A photon, one photon. Okay? Now, it says one photon would have 6.63 times 10 to the negative 19 joules of energy. Right? One photon. You can have multiples of that. You can have 2 times that, 3 times that, 4 times that, but you can't have 1.5 times that, or 3.5 times that, because the energy comes in these packages. Now, do you guys know what a photon is? What is a photon? Yeah, we'll call it a particle of light, okay? Because light is actually considered a wave, and it's also considered a particle, okay? And we'll talk about that in a sec. Yeah. N is 1, because we're talking about one photon. So N is 1. Okay? Good question. Okay. So, let's take a look at the next question. Now, I'm going to ignore this for a second, where it says electron volts. I'm going to ignore that. Alright? So I'm going to explain that in a second. Okay? We're going to do the exact same thing. We're going to compare it now to a photon that is a different color. So let's take a look at a blue photon that has a wavelength of 460 nanometers, okay? Now, E is H over F times N. Because it's one photon, N is going to be 1, alright? Now, we don't have the frequency, but we have the wavelength. But you remembered in grade 11 that B equals F, what? Lambda. So F is B over lambda. So we can just substitute. So we can say this. We can say E is equal to H times V over lambda. So Planck's constant times, joules per second, joules second, not joules per second, joules second, times the speed of light. This is light after all, so I should be using C actually, not V. So that will be what? 3 times 10 to the 8 meters per second over lambda. Well, what's a nanometer? 10 to the negative 9, right? 10 to the negative 9 meters. Okay. So you can see that we're dealing with very big and very small numbers, right? So 6.63 times 10 to the negative 34 times 3 times 10 to the 8 divided by 460 times 10 to the negative 9. So what's our energy? What's our energy? It's probably going to be like 5 times 10 to the negative 19. What is it? 4.3 times 10 to the negative 19 joules. And again, you could have multiples of that, right? But you can't have 1.5 of that because it's quantized. So they're saying that so this particular photon of light will carry with it 4.3 times 10 to the negative 19 joules. Just like an electron will carry with it a particular charge. 1 would carry that, then 2 would carry twice, 3 would carry 3 times. Okay? Now, the question asks for this to be converted into something called electron volts. Okay? And this is for those of you going into physics, this is actually a pretty important unit, and I kind of skipped totally right over it. You may have seen this unit. I think it came up once or twice before, but you're going to see a lot of it going forward. So I'm going to explain what an electron volt is, okay? Well, 1 electron volt would be the charge of an electron, which is, by the way, what's the charge of an electron? What is it again? 1.6 times 10 to the negative 19 C times volt is what? What's the unit for volt? Joules per coulomb, right? So if you do that, you'll notice that 1 electron volt is really the same as saying 1.6 times 10 to the negative 19 joules. Now, the reason why we say this is because, you talk in everyday language, it becomes a little bit tedious to constantly be using, well, hey, George, what did you get as your reading? Well, I got 10 times 10 to the negative 19 joules. It'd be a lot easier to say something like 3 electron volts or 4 electron volts. So what you can do is you can divide. If you want to know how many electron volts, you just take your energy and you divide it by the electron volts, and that's how many electron volts. So, for example, in the calculation that we did before, 4.3 times 10 to the negative 19 joules over what an electron volt is, joules per electron volt. That will give you a number close to, not quite 3, but what is that? Because you'll see the energies are the exponents cancel out, right? It's both 10 to the negative 19. What is it? 2.6? Okay, what did I say? 2.6. So this light carries with it 4.3 times 10 to the negative 19 joules of energy, but also we can just say 2.6 electron volts. Okay, which becomes easier to say. So that's what an electron volt is. Okay. All right. That's so far. Is that hard? That what we just looked at? It's pretty easy. So you should be able to calculate the energy of any photon as long as you know the frequency or the wavelength, and you should be able to convert it into electron volt just by dividing by 1.6 times 10 to the negative 19 joules per electron volt. Okay. Okay. Now, the other simulation I wanted you guys to look at was the photoelectric effect. Okay. So let's take a look at the photoelectric effect. Okay, so where's the photoelectric effect? Quantum phenomena, photoelectric effect. So here we go, right here. Okay. Run. Open. Okay, so, you guys play around with this? Okay, so let's take a look. Right now, so the idea behind the photoelectric effect is you take a light and you shine it on a metal conductor, and we just saw that light has energy, right? That comes out in these discrete packages. And if the amount of energy is high enough, it should be able to liberate electrons. And then the electrons will move from one plate to the other plate. So right now there's no light. Remember the intensity, so do you guys remember your waves in grade 11? The intensity is what? What's the intensity? What would define the intensity of a wave? What would define it? So if you recall, so a wave is something that does this, right? It oscillates back and forth. So imagine that this was like waves in water, okay? What would be the difference between these two waves? So we'll call this wave A and we'll call this wave B. Which one has a higher frequency? B, right? Because frequency is number of oscillations per unit of time. But which one have more energy? It'd be A or B for waves. So here, I'll give you a visual, okay? So here you are. There's you, and you're on the beach, and there's a wave coming at you. Look at that wave. Wow. Okay? In fact, maybe there's many waves coming at you. Okay? Versus one wave coming at you. Which one would have more energy? Which one would you be worried about? The one that has lower frequency but is higher in size? That would be the intensity. That's the amplitude of the wave, right? So that's the intensity of the wave. For waves, it's the intensity is the amplitude of the wave. That's the strength of the wave. Yeah? Now, there's a reason why I'm telling you this. Because it has to do with this, because this was a bit puzzling. So the intensity is the strength of the wave. So what should happen if we increase the brightness? So right now there's no light, so nothing's happening. So let's add a bit of light. So you can see we've got some light shining on the metal conductor. So the light has energy. So what's going on is the electrons are absorbing this energy, and they're absorbing enough of it to be released from the surface of the metal. Okay? And you can see that we can actually measure the voltage or the energy of the electron. Okay? So right now, there is the energy of the electron in electron volts, by the way. Okay? Now, what happens if we increase the intensity? Well, you should see more light, more electrons coming through. So you see the difference there? So if we decrease the intensity, less electrons are coming out. If we increase the intensity, make it brighter, more electrons are coming out. Okay? Why? How do you explain that? No, we're not changing the frequency. So that will be the next part. All we're doing is we're changing the amount of light. to give it that way. There's just the amount of light. So when something is brighter, that just means it's more light. That means there's more photons striking the metal. So the more photons there are striking the metal, the more photons there are to liberate the electrons. Therefore, as it becomes brighter, more photons are striking, more electrons are being liberated. As we make it less bright or duller, less photons are striking, less electrons are being liberated. But you'll notice something about the speed at which these electrons are traveling. Okay? I'm going to keep the intensity constant. Okay? But I'm going to change the frequency of light. Okay? So what's going on here? Actually, there comes a point where we can make the light as bright as possible, but look, nothing's coming out. Why not? We just, before we made it brighter, more electrons came out, but what's going on here? Alex? Beautiful. We changed it, I changed it to red light. Now, here's the thing. According to the equation we used, E equals H times what? F, right? Now, red light has higher or lower frequency than blue? Lower. What happens then is the photons of light that are red have less energy than the photons of light that are blue. So when we switch to blue light, why does blue light liberate the electrons but not red light? What's that? They have higher frequency, that means they have higher what? Energy. So think of it as a collision, right? No, we did momentum. So the blue photons have more momentum. Momentum. When I use the word momentum, remember momentum is m times v, right? We'll talk about momentum of a photon tomorrow, not today. But they have basically more momentum because they have more energy. So they can liberate the electrons, whereas the red do not have enough energy. They don't have enough momentum to knock out the electrons. So you can see a relationship. As we move the light towards, now take a look at this. This is the energy of the electrons coming out. Take a look. You'll notice it goes up. As the wavelength gets shorter and the frequency goes up, the energy goes up with it. And if we decrease the intensity, you'll notice something. Take a look at the energy of the electrons. Look how they're streaming. The energy of the electron is not affected by the intensity of the light. What is affected is the number of electrons coming out, the current, that's the number of electrons coming out, but the energy of each electron is constant, regardless of the intensity. Now we have a problem. Do you guys see what the problem is here? What's the intensity of a wave? What do we say the intensity of a wave is? What do we say the intensity of a wave is? It's the height of the wave or the energy of the wave, right? Well, we got a problem now. We got a huge problem. You see, the huge problem is this. The intensity of a wave is the energy of the wave. What I'm showing you here is that the intensity is not affecting the energy of the electron. How is this possible? So Einstein looked at this and made a conclusion. You know what he said? Actually, see if you guys can figure out what he said. What do you think he said? Yeah, we'll fill in the blank. He said light is blank a wave. He said light is not a wave. It has wave-like characteristics, but in this case, it's not behaving like a wave. It's behaving like a particle. So we can't look at the intensity of the light and think of it as a wave and say that if it's brighter, it has more energy. You can't think of it this way. Okay? So the photoelectric effect actually proved that light is also like a particle. And that the frequency of the light, as we saw, determines the amount of energy of that particle, not the intensity. The intensity is how many particles, but the frequency is how energetic those particles are. Does that make sense? Do you have any questions about the photoelectric effect? In case I ever ask you to explain it? No? I'm kind of hoping that we can investigate this with solar batteries and different types of light. That's why I was playing around with that. But I gotta find solar batteries. Okay, so, let's do one last calculation. Actually, two last calculations. Then we'll call it. Okay. So we're gonna figure out, so the photoelectric effect, this is an equation that summarizes the photoelectric effect, okay? What do you think this is? EK, what's that? Yeah, this is the kinetic energy of an electron, okay? This, we saw, was what? What's Eject? That's just energy, right? What's W? W is the amount of energy required to remove the electron from the metal plate, okay? So, think of it this way. Imagine I have a surface, and I need to remove something from the surface. And it takes 10 joules of energy to just remove it from the surface, okay? But I apply 20 joules of energy. How much kinetic energy would it have then? It would have 10 joules of kinetic energy. Does that make sense? Right? Because some of the energy went into removing it, and then the rest of the energy was left behind in terms of its kinetic energy. So we can look at it the same way here. Okay? So what would be the minimum frequency of a photon required to eject an electron if it took 3 electron volts to remove it from a metal? Okay? And by the way, every metal would be a little bit different. So I don't know what metal this is. Okay? So how much energy, well, sorry, what's the frequency of light? So here's our equation. Equation is EK equals HF minus W. What are we looking for in this case? What do you think we're looking for in this case? Because we're looking for what? Frequency, right? Okay. What do we have? What do we have here? Do we have H? Yeah, H is a constant. So Planck measured this. Right? All constants are experimentally measured, right? So he measured, so we have this. This is given. Alright? Even though it's not given, it is given. 6.63 times 10 to the negative 34. The work function is given too. We're told it's 3 electron volts. Now remember, 1 electron volt is what? 1.6 times 10 to the negative 19 joules. So 3 of them would be 4.8 times 10 to the negative 19 joules. So we have the amount of energy, we have W. What do you think EK is? This is where it's important to really read the question. So Cassian came in and was asking me a question during my break. And it's very important that you read the whole question, right? Make sure you read every little word, because sometimes one little word changes everything. So, it says minimum energy, or minimum frequency. So what are we going to assume EK is then? What's that? Not 4.8. That's how much energy required to remove it. 0. It's the minimum energy. So in our previous example, if it takes 10 joules of energy to get something off the surface, if we apply 10 joules of energy, we remove it from the surface, what's left over? Nothing. So that means the thing would be removed from the surface and would just be floating there. It would have no kinetic energy. Okay? So we're going to say EK is 0. Well, if EK is 0, then what can we do? We can set, if this is 0, we can set HF equaling W. And then we can solve for F. Because F would be what? W over H. So the work function was 4.8 times 10 to the negative 19 joules. H is 6.63 times 10 to the negative 34 joules seconds. What do we end up with as our minimum frequency? 7.2 times 10 to the what? 14. Now, if you want to know what color of light that is, what you could do, and I'm not asking in this question, but I could be asking in on a quiz or a test. How would you figure out what color? Imagine the question is, what color of light is that? You'd be like, okay. What do I do? Yeah, unless you had a chart that showed you the frequency of light, but in the example I gave you, it was the wavelength of light, right? So then you would just simply take this equation and then isolate for lambda, and then you would be able to figure out the wavelength. So that would be, what is exactly? 3 times 10 to the 8 over 7.2 times 10 to the 14. 4.1 times 10 to the negative meters. So that would be the same as 410 nanometers. So 400 and I closed that window, didn't I? So 410 nanometers would be okay. Where's my Blackbody Radiation? Oh, right here. Sorry. 410 nanometers would be. Oh, this is not a scale, anyways. Okay. It would be blue light. It would be. I thought this had a scale on it for some reason. So it would be in this week, right about here. I don't expect you guys to memorize the different colors of light and the wavelengths. But if I gave you a chart, it's reasonable for me to say what color of light would you need to eject an electron. But I have to give you the chart. Okay, last one. Calculate the speed of an electron ejected by a photon of light from a metal called cesium. So the work function is 1.95 electron volts. Okay, this will be our last question. So again, electron volt, we're going to convert that to joules. So that will be 1.95 times 1.6 times 10 to the negative 19. So what is that as in joules? That should be close to 1.95 times 1.6 is what? Close to 3.1? Yeah, and 10 to the negative 19. Okay, so here's our equation, right? Now, this thing will have speed. So the kinetic energy will not be 0. So EK is equal to HF minus the work function. The wavelength is 3 times 10 to the negative 7. So H is 6.63 times 10 to the negative 34. And if you don't have a frequency, you could use V over what? V over lambda, right? So V over lambda would be 3 times 10 to the 8 over 3 times 10 to the negative 7. Okay, so there's your V over lambda. Okay, V over lambda minus the work function. All right. It's light, right? It's light. So light all travels at what speed? Yeah. Now I'm saying that light travels at always at 3 times 10 to the 8 meters per second, but we're talking about what medium though? If you remember in grade 11, the light actually will slow down in different things like water or glass. You guys remember doing the refraction? Okay. So here, when I say it's the same speed, I mean in a vacuum or air. Air is considered very similar. So what is this? What's the kinetic energy? (3.53 times 10 negative 19). Okay. So that's how much energy the photon has. Now, that's not the speed though. What's the speed? Well, we got to use the other kinetic energy equation, which is 1/2 mv squared is equal to 3.5 times 10 to the negative 19. Now, what is the m of an electron? It's really tiny. I'm going to get rid of the half, and we're going to divide by m, and then we'll take the square root of everything. Yeah, so what's the mass of an electron? Not to charge an electron. What's the mass of an electron? Someone has to Google it. I don't remember. I think it's times 10 to the negative 31. It's like a really, really small number. Yeah, what is it? 9.1 times 10 to the negative 31. Okay. So 3.5 times 10 to the negative 19 divided by 9.1 times 10 to the negative 31 times 2. And you take the square root of that. So just by looking at it, the answer should be like 10 to the 6 or 10 to the 5. It's going to should be 10 to the 5, I think. What is it? $880. So that would be 8.8 times 10 to the 5 meters per second. Okay, so not even like a fraction of the speed of light, a very small fraction. Okay, ladies. So there's your intro to some basic quantum mechanics calculations where we looked at the energy of photons. Okay, and then tomorrow we'll talk about the momentum of a photon. And by the way, you should be asking the question, how can you be talking about the momentum of a photon? Because, sir, you always told me that light has no what? Light has no mass, and our equation for momentum is P equals m times v. So how can we, so sir, can I skip tomorrow because light has no mass and therefore tomorrow's lesson would be useless? We can still talk about the momentum of a photon, and you'll see tomorrow how we're going to do that, okay? Alright ladies, so let's end there. The end.